Hello? Okay. Okay, so let's start the afternoon session with Professor Keh-fei Liu from the University of Kentucky and Lawrence Berkeley National Lab.
Right.
And he's going to tell us about his exciting stuff. So.
Yes. Okay. All right. Is there a pointer? Okay, the pointer. This point and this is okay. All right. Can you hear me? All right. I'm going to discuss some of the very simple concepts, and this talk is mainly for graduate students. All right. So the concepts like the mass, the energy, and pressure, and then I'll be mostly concentrate on pressure, which is less discussed. But even with mass and energy, there has been in the literature and even in our fields of QCD, and there have been some confusions and so on. So I'll address some of that and then go on to finally a trace anomaly form factor in the pion mass and the pion mass puzzle. All right, so I think we all know that one of the major EIC goal is to understand where the mass of the proton come from. Of course, we talk a lot about the spins and so on, but mass is another issue which is one of the EIC goals. Now we know the Higgs exists. It gives a U quark, this 2 MeV or so, D quark about 4.7 MeV or so. But we know the proton mass is 938 MeV. You know, this is only 1%. So where does the rest of the mass come from? Okay, even that question, I will question that question, all right, as we go on. All right, so let's just a slide looking at the concept energy and mass, all right? And usually written down is E equal to mc squared. Now you look at that equation, and it says, well, energy is mass squared. Does that mean really when the energy increases, we know energy will increase, so you move, that's the mass increase. In fact, some of the literature does say that. Now it's pointed out by Okun, who gave a series of talks on the subject. Now actually, Einstein was a little confused at the beginning. It turned out in 1905, he wrote a paper saying it's rest mass, which is the energy. So you can see that from the dispersion relation and squares and so on. So energy at rest, and that's the mass, right? But however, it does not mean energy and mass are the same thing. Just like F equal to ma, it does not mean the force is the same as ma. You measure F in one set of experiments and ma in another set of experiments. It happen to be equal. All right, so one example is that you'll find that the energy you can decompose into different components, but mass you cannot. One example that Okun gave is, so E plus E minus goes to 2 photons, right? We know the 2 photon system has a mass of 2 MeV because energy conservation. It's not the sum of 2 photon masses, right? Even you take an apple, for example, you cut it in half, it's not the sum. The mass of the apple is not the sum of the 2 separate apples because you're breaking some of the molecular bounds. So the mass, you can describe the energy in terms of the quark and gluon components. Mass you cannot, right? You just cannot decompose mass, right? So that is a concept which I think was not very appreciated in our community. Now, of course, as a mass is a scalar, and energy is a component of 4 vectors. E and P are additive, but not mass, okay? So here you can see that, of course, in general relativity, the source of that is the energy momentum tensor. And finally, you can see that, as Okun mentioned, the relativistic mass is a misnomer, and rest mass is redundant. Okay, mass is just mass. All right, if you're interested, you can look at some of these papers. Now, let's go on to the QCD system, which is quite unique in that it has an expression for mass and an expression for energy. Now, that's not true for many of the systems we know of. For example, you calculate many-body systems. We say, well, we'll calculate the mass. But that's not what we do. Actually, we calculate Hamiltonians. Just do variation calculation, you get the rest energy and call that mass. In lattice calculation, we never calculate energy, the mass of the hadrons, we calculate this energy by looking at the lattice correlator, which is exponential of the Hamiltonian, which Hamiltonian is the energy, and then you calculate that energy in a rest frame and call that mass. Right? So it's not simple. Except for QCD or QED, we don't really know how to calculate the mass, but we also should calculate the energy. Okay, all right, let's go on. In the hadron mass case, there's energy moment tensor, which is made up of the quark part and the glue part, right? And the trace, the mass of this can deduce from the trace. The G mu nu of the T mu nu, for example, in the forward matrix element has this expression 2p mu p nu. Therefore, when you take this and normalize with the moment states, you get a mass in any frame, forward matrix element. So that's a direct calculation of the mass. Now, the expression, of course, the trace has in QCD, besides this classical term, you have a trace m side by side. When the quark mass is not zero, you have this term, but you in addition, because the conformal symmetry breaking, the coupling constant runs, or scale symmetry breaking, you have an anomaly term, which is derived earlier in the 70s, I think. You have a trace anomaly term, beta of the 2g times the g squared, and m side by side mixed in here with the gamma m, which is the mass dependence on the coupling constant. All right, so both of them are renormalization group invariant. This renormalization group invariant, you can say, well, these are made of two terms because both of the renormalization group invariant, they can be measured experimentally, but these are not a separation. You cannot say, well, this is the glue part and the quark part. That, as I said, you cannot separate on the mass in that way. So let's look at what they have. Now many people have calculated the sigma terms, the pi nucleon sigma terms, put side by side, develop the nucleon mass. You have a strangeness, okay, strangeness give you 4.3%, and sigma pi and sigma quark U and D give you 4.9. So altogether, it's like 9%, and the remainder is the trace anomaly accounts for 90%, 91% of the nucleon mass. Well, this is for light quark. You can also consider the heavy quarks. For the heavy quark, you have a C and B and D, T turns out to contribute about the same amount because you can see that when you look at the heavy quark, you do heavy quark loop expansion, and the first term turns out to be G squared with the alpha sub s here, which is just the first order term of the beta functions. So therefore, you can see there, just shown by Schiffman and company, that there's a decoupling theorem. When you take all the heavy quarks and the anomaly together, that should be 1 over mh. Because when you introduce a heavy quark, you reduce the coupling constant, the beta function. Therefore, the trace anomaly will give to compensate for that. All right. So you add the heavy quark together and glue, and that's almost the same constant. So either way, you can accommodate that, depending how many flavors you're dealing with. All right, so that's mass. Now, how about energy? On the other hand, energy is different in that sense, because it's been shown by G and so on, you can decompose the energy moment tensor because it's in this is a Billet-Fonte form. This is a symmetric and rank 2 tensor. You can write that in the traceless part and the trace part. I will emphasize the trace part is a G mu nu, okay, proportional G mu nu. And of course, you want to look at the energy, it's the T00 component of that, which is the Hamiltonian. And if you can look at this decomposition, you can see that you can write that in the quark piece, all right, the gamma and D derivative, and take the trace out as traceless part. And you have a trace, the glue part is already traceless. It's B squared, E squared. Therefore, this is the quark energy. This is a glue field energy, right? The B squared, when you do that, is in the vacuum. Now here it's in the hadron. And in addition, you have a quarter of the trace part. And that's and the trace has a trace anomaly, which is, and then the lattice people, how to know, can handle that. So the rest energy is the sum of these terms. And you have a quark energy, glue energy, and the trace anomaly term, all of that. Now, turn out, of course, since the traceless, energy momentum tensor, that in the deep analysis scattering or the parton model, that corresponds to the second moment of the momentum fraction of the quarks and gluons. So this one gives you, it turns out it's a 3/4 of the momentum fraction of a quark and 3/4 of quark momentum. And the trace itself give you, remember, a quarter of mass. Remember, the trace itself give you mass. This is like 1/4 of the mass. So this is the energy decomposition. You can see it's totally different from the mass that we expressed here. Turn out at the rest, they are the same. The value is the same, okay? All right. Given this, you can look at this following situation. You can see the 3/4 comes momentum fraction, or quark energy, glue energy, if you wish, or you look at the taking the numbers from the global fitting of the parton distribution function, you get the momentum fractions. Okay, so you have U quark momentum fraction, D quark momentum fraction, strange quark, and charm, and so on. I should mention that once you do that decomposition, then it becomes a scale dependence. Earlier, the mass does not depend on scale. It's a reionization group invariant. But here, when you do the decomposition of the energy, the quark energy and glue will have the momentum, the scale dependence. Now here at a 2 GeV, we took the number from the CT18 fitting, and you can see that the glue part is 31%, and then the quarter is the mass part, the trace part, which is of course mostly the trace anomaly. You have a sigma term and a strange term, a strangeness. Now, of course, you can also go on with different scales, as I said, because of scale dependence. You go to the weak scale, 250 GeV, you can see that you have all of a sudden the heavy quark becomes more significant, and the incomposition of the glue also increases. It's the valence part which becomes smaller, and that's, we all know from the evolution, the valence contribution goes into the C and the glue. A quarter remains the same, right? But except you may have a heavier flavor contributions, and the trace anomaly is getting smaller. So that's what we have for this the decomposition, 3/4 momentum fraction, 1/4 of the sigma terms, and so on and so forth. All right. So that has all been these are calculated. Mostly I'm taking the experimental value, the global fitting value, but except for the sigma terms, I'm taking a lattice calculation. All right, well, let's go on. Another way of looking at that people have talked about in this conference is gravitational form factor. Right? The gravitational form factor has the following form. It has for the nucleon, it has a form factor called a form factor called a B, which depends on the gamma mu and p nu, and some dependence of here. And then there's compared to the, well, A and B, you can see it's almost like the electromagnetic form factor, which is a vector current. Here are the two indices. You have an extra piece of the piece and an extra piece of the moment. And otherwise, the structure-wise is very much like F1 and F2 in electromagnetic form factors. And there's a new piece called a D form factor, and there's a new piece called a C bar and G mu nu, which is, remember that the G mu nu part, which is the metric term, which turned out to be very important, and many people ignore this. This has turned out to be one of the most important ingredients I'll talk about today. And it's been shown that the forward limit, A, is the momentum fraction, and B is the angular momentum fraction. As Neomani mentioned, that you have a sum rule, right? The quark and glue sum up the momentum fraction to 1, and angular momentum sum up to 1/2, for example. And D, you can see it doesn't contribute for the forward limit because it has a momentum dependence. But if you look at the spatial distribution, it has to do with something with the pressure. Okay, C bar also, okay? C bar people have ignored it before. Turn out it's the pressure volume work, which I'll mention that. And this is just related to the TII component of the energy momentum tensor, and the D is related to the off diagonal. There's the different stress of the shear stress and so on. Okay, but these are all pressure. D and C are related to pressure. Now when you look at that, you look at a T00 component, let's say, then you find it is A quark and glue, and plus C bar, because for the B part, for the forward matrix element, B and D do not contribute, you have A and C bar. And the mass, which is the trace, and is A plus 4 C bar. Okay, and the C bar is this. Now, so we need to set out and solve for C bar. So what is a C bar? You can look at this. When you look at the forward matrix element, the C bar, 3 times C bar, is the TII, which is the T mu mu minus T00. Okay, that involves A and the C bar, and you can solve for it. Solve for it, what I find the expression of C bar for the quark and glue together is quark is a quarter of the trace anomaly and sigma term, and minus a quarter of the momentum fraction. Each one, of course, sum up to 1, therefore it's 0. Okay, and this is one of the reasons people drop it in many expressions. So I'll show you that it's not proper to drop it. Anyway, so what this means is that you have some pressure, associated with pressure, and some other pressure which are balanced out. Okay, and this is consistent with the fact it has to be this because of energy momentum conservation. The conservation of the energy moment tensor will demand that C bar and forward matrix element is 0. And also this one, when you look at all the form factor with the momentum transfer and so on, you can still use this to demand that A, B, AD, and sigma are somehow related. Okay, now let's go back to the E0. So we said E0 is A plus C bar, right? Plug in the C bar there, and then we'll find that it's a 3/4 of the momentum fraction and a quarter of the trace anomaly. Just exactly the same as I said, start of Hamiltonian, all right? And the T mu nu is this minus 4, so the A drops out. Remember, this one is 4 times, this is 1/4, so this term drops out, you have only the trace part. Therefore, what I've shown is that when you do the gravitational form factor, forward matrix element, you get the same expression as the mass, and also the same expression for the energy. And that's not true in most of the places of literature, right? Which I'll show you why that's the case. What people would do, usually would drop the C bar, then the energy becomes A, and mass becomes A, which is numerically not wrong, because it's A sum up to be 1. But physically, as I'll show you, it does not make sense. And you have to also, why would I start from Hamiltonian? I get one expression. When the gravitational form factor, I get another expression. It needs an explanation, and people don't explain that. Okay, so this is just show some consistency. Okay, the next, we're going to talk about the trace anomaly, its role in the hadron mass and energy, and particularly in its energy in equilibrium. All right, so let's first look at the trace anomaly and the strain tension in the germanium. Heavy quark, we know the heavy quark better than the light quarks. We know there's a linear potential. And what happens is that usually the potential comes from that you have some energy density, and you have an area which is constant, and you pull the quark and that quark apart, it's proportional to R. So that's the strain tension times R. In fact, you can look at it this way. There is a proof that if you look at the glue part of the trace anomaly, and you fold it with the Wilson loop, large T, large T separation and large R separation, and divided by this loop here, it gives an expression which is a potential plus R dVdr. Remember, we look at the Polyakov loop, and that gives me a potential energy, but this one's another one has an extra term, dVdr. Now, for the germanium, suppose the V we know is more like linear, so this gives the 2 times the sigma and radius of the germanium. And that one is the same as to put in this term in a CC bar, instead of putting the Wilson infinite heavy quark limit, put that as CC bar states. And this one we can calculate. The reason that we can calculate, we can use the sum rule of the H beta, is beta of the 2G part, is the germanium mass, which we can calculate, actually calculate through its energy, rest energy, minus 1 plus gamma and then HM. HM is the sigma term for the charm, MC. And then gamma M, we'll take that to be 0.2, so they can get this expression. And there was one calculation on the lattice using the charm. I took the numbers 190, they give me 199 MeV. And I know the R coming from a potential calculation and so on, and plug that in, I get a sigma, string tension 0.153 GeV squared. And there is a sophisticated Cornell potential fitting for the carbonium spectrum, botanonium spectrum, and look at all these very detailed ones. And for the carbonium, there's string tensions. It's very close to what I have. So what this says that in the carbonium system, we more or less know it is you have a linear potential, all right? And this is something which we'll come back to later on. All right, now let's go on to discuss the pressure, the resonant energy, and so on. There turns out to be an energy equilibrium correspondence, I call it EEC. What this says is the following. If a rest energy, remember it's a 3/4 of this momentum fraction, or quark or glue energy, and a quarter of this trace anomaly sigma term. On the other hand, the pressure, TII, is the, remember if you look at fluid dynamics, so T00 is energy density, and this T0I is a momentum flux, I0 is energy flux. This one is a normal stress, diagonal. The off diagonal is a shear stress. Okay. So let's concentrate on the normal stress. Normal stress is just pressure. Now that is -3 of that. Okay, but being a pressure, so if we look at the pressure volume work, so d over dv in first order at 0 temperature, the first thermodynamic law of thermodynamics, d over d times v is this guy here. And what do we have? We have a quarter of this guy and minus quarter of this, which is 0. Now, compared to energy, you can see that the coefficient of this one is a 1/3 of that, and there's a -1. But remember, there's a negative part for my pressure. So actually, this is a -1/3 difference in this one as the same coefficient for that. Now, however, of course, it's energy as a function of volume. So from this information, I can induce a volume dependence of these terms. Okay, let's go on to deduce the volume dependence. So what's the energy in terms of the volume, the hadron volume in that case? All right, before I go into that detail, let me give you a few examples where we know some of the answers are, right? First of all, there is a generic bound state energy and equilibrium correspondence. Let me give you some examples. One thing is hadronic models. The first one is the MIT back model, where the back constants was introduced through the metric term in the energy movement tensor. Remember, that's the same place we introduced the trace anomaly term. So B is really the trace anomaly, except the MIT the back model was invented in 74 or so. The trace anomaly was invented about the same time. They don't seem to know each other. Okay. All right. So you can see that you have a volume, the B time, the back constant times volume, and energy of the quark and glue is 1 of R, V to the -1/3. When you solve for the back model, what do? For a different state, for the proton, for the rho mesons, you see 3 quark or anti-quark, you solve the glue part from this, solving for this, and you take derivative. The only variable here now is volume, or the R. You take a derivative with respect to R, because the one is rising, the is falling, and that gives you the give you the energy of that state, the mass of state. So that means this one is the energy and pressure, if you wish, equilibrium conditions. For the skyrmion, it's something here, you can, direct theorem, you can scale that. 1 goes 1 over lambda, it goes lambda. So there is a minimum where you can find the energy is. And of course, there are also other models. Sorry? B is a back constant. Yeah, B is a back constant. As I mentioned, I look back now, I find out B was introduced through the metric term, an energy movement tensor. Okay, now let's take the nuclear atomic systems with R to the M potential. Right? Energy is V plus V, T plus V, and the equation of state, all right, is Well, you call it equation state, you can just scale the system, right? With say a very sophisticated variational potential, just for dimensional analysis, the kinetic energy is 1/r², some constant. And this one is r to the nth power, okay? And take your equilibrium, which is the force times r, and this r minus is 2t minus nv. So the 2 is related to that coefficient, and n is related to that. That shows the kinetic energy and this power dependence. That shows this should have been in this form. And this is what? F of r is the Vera theorem. So the energy, the EEC I was talking about is the Vera theorem for a bound state. In fact, there is a proof, I didn't have time to show it. It's in the paper that I showed up in the very beginning. There is a proof of in general, many body system with pairwise interactions. The TII, the pressure, is the expression of P times dV, d over dV, and that expression for the TII is exactly the same as Vera theorem. Zero temperature, yeah, talking about zero temperature. First order, yeah, it's just pressure balance. Like in the chelmonium, right, this is the chelmonium, you have a balance between potential energy and kinetic energy. That's it. It's very as simple as that. But we have not now introduced the gravitational form factor to show that. It's not as sophisticated as they are. Okay, so now let's go back to the QCD we have. The rest energy is a set 3/4 of this, 1/4 of that. The pressure balance of this thing is a quarter of this minus quarter. All right. So if I take the energy to be volume to the certain power, and the V dV is just the moment of x. So the coefficient just shows the coefficient of x. So if I decompose the energy into a triplet part and singlet part, this is the singlet part, which is the trace anomaly and the sigma term is proportional to volume. And this one is proportional to volume minus 1/3. It's just like a back model. Where's the back? This is the back constant, and this is the quark and the glue energy in the back, and so on. It's like 1/r. All right, so that the PV is equal to 0. All right, so now comes to the interpretation. Why is that the case? Now we said we have two terms, which is from the balance. One term is proportional volume, the other term is volume to minus 1/3. And this epsilons are just energy constant, E of dV. So what is this energy constant? Constant energy, where does it come from? We know that in QCD, there's a vacuum condensate of the glue condensate, because it breaks the conformal symmetry breaking. So there is the vacuum energy is beta over 2G. The beta is negative, right? So this is the F square in the vacuum is negative. And what you do in this one is that I have a vacuum condensate, then I put a hadron in it, either a QQ bar or 3 quark, make a dent, make a hole, all right? That presumably is, you have to take energy relative to the vacuum, where the vacuum is positive, is negative. It turns out the whole expression is positive. The energy, what's the volume? Volume is just the energy, the vacuum energy divided the total energy divided the vacuum energy. So you have a constant, you make a hole in it, that energy is energy density times the volume. Because this one, dimension-wise, is dimension 4 operator, which is energy per volume. Okay, so the energy density. So this one, that is like I have a bubble, you know, if an ocean of gluon condensate, I make bubbles and put 3 quarks in it, some glue on it, and that when you displace the vacuum, it creates a positive trace anomaly, which is balanced by the energy of the quarks. The quark and glue has a kinetic energy and potential energy. These two pressure are balanced. And the same pressure here, same as the chelmonium, where it's a vacuum condensate energy times area times R. Whereas if it's shown lattice, some lattice calculation that A seems to be, when you look at the pull this thing apart, the cross-section part does not seem to change. So therefore, the energy is proportional to the separation. Well, this confinement, as I said, is very much like this volume confinement, the linear confinement. It has nothing to do with the color confinement. People have talked so much about color confinement. You have a dual the superconductors, magnetic monopole, and this. This is not about that. The confinement that I was talking about is at the same level of this thing here. Why is it confinement? The thing is when it's volume, right? You take the volume, the pressure is volume, d volume, d energy, d volume, right? So and it's a negative term. So what you have is when you take a derivative, you find the pressure from this one is negative and constant. Just like the potential energy here is when the force of this thing, of the charmonium is constant and negative. Same thing, right? So therefore, that's confinement. Any questions so far? Okay, now, let's go on. For bound state, the decomposition of the rest energy with relevant and meaningful physical constants are those with the EEC. For example, as I said, you take the gravitational form factor and you drop the C bar, as people do in the literature, C bar 0. So my energy is A, right? Momentum fraction, which is numerically it's not wrong. But as I said, it's like the case where you consider Vera theorem in the Coulomb potential, H plus V, and we have from the Vera theorem, 2 times the T is minus of the V. Right? So you can say, well, you can say that my energy is negative the potential kinetic energy, or a half of the potential energy, which is numerically correct. But it doesn't have a physical meaning. Remember, the physical meaning of this is a balance. The total energy is balance of the kinetic energy and potential energy. Both has to be present. So you cannot drop C bar, in other words. All right. So when you take the trace of this thing also, you need to put to the C bar to get a semi-expression, have both kinetic and the pressure energy. When you take the volume dependence of that, then you have a pressure balance. Right. Here you don't have that. So it's not the same thing. All right, let's go on to a system that's probably better known in the type 2 superconductor. And we know there are vortices. Type 2 superconductor is following. The phase diagram is a magnetic field and temperature. When the magnetic field is not strong enough and temperature is below the critical temperature, then you have a NISER effect. All the magnetic field are expelled, like type 1 superconductor. But when you increase the magnetic field, at certain times, some of the magnetic field will penetrate through it, and that form a vortex. And when it's large enough, then you destroy the superconductor. So during this phase, and you can see that the vortex look the following. You have the magnetic field inside here. Inside this one is a normal phase, and therefore you have magnetic field which is penetrate through it. But then it goes down as it goes deeper into the superconductor. On the other hand, you have a superconducting phase. You have a Cooper pairs. Cooper pair is destroyed here, but it becomes larger in this case. All right. So this can be explained by the Ginsburg-Landau equations, where the phi squared, the parameter square is the number of Cooper pairs, and they have a London penetration depth, which is like how much this one goes in here, how much the B field can go in there. This coherent length, how much that the superconductor phase will be correlated to that. When the kappa, the value of this ratio is greater than 1 over square root 2, then you have a type 2 superconductor. Right? So how is it related to the hadrons that we want to talk about? One thing we can look at that is from the, again, just the energetics. Right? The energetics is the following. You have a part which is the cost of condensation energy. What's the cost of condensation energy in the condensed matter sense is that I have a vacuum, right? I have a Cooper pairs, which has Cooper pairs as a lower energy, has a gap. When I make the vortex in it, that lifts this thing, so it's a cost some energy to do that. because it's like here, my energy times the gap times the density is like this, but I'm making a depleted this here. Otherwise, it'll be all the way negative, right? Another one is the magnetic energy. Magnetic energy is B squared, right? There's no electric energy here in superconductors, and that's integrating over all these things here. And then you have a supercurrent, kinetic energy. The electrons will move around the vortex to produce a magnetic field counter the external magnetic field, and that's the fermion energy. So, oops, sorry. Okay, now there's a variational model, which is well known in this field, that you have some parameter. R is just the core of this thing here, and rho is the two-dimensional radial coordinates. When you look at the energy, which is the energy per length of this thing, because it's a vortex which goes all the way, and taking just the energy per length, it turns out the free energy, in this case per length, has the first term, the Fs. The cost of energy term is proportional to the service term. And then you have altogether is 1 over r prime. The kinetic, the V squared, and the fermion energy is 1 over r squared. And what you do, you find out the variational equation, you vary that with respect to r, that the FL is area divided by area 0. That leads to an energy, a pressure term or EEC term, which cancels out, with this contribution, that contribution cancel out that one. But notice this one is proportional to, if you include the length, it's proportional to volume. So there's a one-to-one correspondence that we're talking about. Now, if it's a superconductor vortex hadrons, you have Fs, which is cost of energy. Here it's a trace anomaly. It's come from because you're replacing the vacuum condensate. Because of the presence of vacuum condensate, you get this, and you make it in volume. This is proportional to surface times L, and this is proportional to volume. Okay, and this magnetic field, same magnetic field because of E squared and B squared. You have a superconducting currents. This is the quark energy that we have, and you have a sigma term, ME here. You don't have the here, but you have here, but not in the electron, but in the side by side, in the non-relativistic limit is just a number operator. The number times the electron mass, it's just a constant. So you just scale out of the problems. So this one you have then you derive the negative constant pressure from Fs. And this is negative constant pressure from trace because the confinement is due to the superconducting condensate, and the confinement due to the gluon condensate. You have a gluon condensate, which comes from the conformal symmetry breaking. You make a hole out of it, you have a confinement. The confinement is identical in that sense. Now, go on to cosmology constant. Remember that Einstein introduced cosmology constant to balance the universe. He thought the universe was going to collapse. And what he did is introduce a lambda g mu nu, which is lambda is energy density, a constant energy density. And this is the Ricci tensor and so on. And on the right side is the energy momentum tensor, which is the source of the energy moment of the general relativity, all right? Now, suppose you do this. You put this term, instead of left side, put it on the right side. And consider that as an extra term of the energy momentum tensor. So it's very much like the QCD where you have a trace anomaly. And this could be some anomaly from somewhere, all right? So, but there's a difference between the QCD and general relativity in that the Friedmann equation of this is the following: some scale parameter. This is a Friedmann-Robert and Walker scale. The double time derivative divided A is 3 times of that. Okay, and it turns out that the trace anomaly behaves like a hadronic tensor. That may show up. Am I done in time? I'm sorry, I'm so far off. Okay, anyway, one speculation was that suppose outside the universe, there is a condensate. We don't know where it comes from. Nobody knows where dark energy comes from. Suppose the universe is embedded in the outside with some condensate, some gravitational anomaly, and so that the outside is negative, therefore inside is positive. somehow for the selecting, Einstein's gravitational, the universe will be confined. But here, because you have an additional pressure term, which is negative, that makes it expand. All right, I don't have much time here. I guess my time is up. Probably don't have time for the pion mass. You can read about it. But one thing I wanted to do mention is that there was a puzzle as to why this thing would go to, the pion mass goes 0. This one, why is a trace anomaly, which is from conformal symmetry breaking, why it doesn't have anything to do with chiral symmetry? Why does it have to go to 0? How does it go to 0? Turn out the form factor changes sign. It's been calculated recently, just post, and it has a radial distribution which changes sign. So the trace anomaly is negative inside, positive outside. When you come to chiral limit, they cancel. That's how the trace anomaly term becomes 0 at chiral limit. But we don't know why still. All right, that should be all. Okay.
We're really over time. We have maybe time for a quick question. Someone wants to, yeah, Santa.
So you mentioned about these vortices and trying to relate to the mass problem.
Yes.
But vortices also were speculated to be a cause of chiral condensate formations or chiral symmetry breaking.
Right.
Can one relate this to the mass problem?
I didn't have, I has a slide of that. The vacuum condensate, but in the Cooper pair come the gauge symmetry breaking. Here we have chiral symmetry breaking and conformal symmetry breaking. So the origin of the condensate is different. One is from the, as I said, Higgs and so on mechanism, and the other one is but the fact it doesn't matter where you come from, as long as you have a constant vacuum condensate, and that creates a constant negative pressure that is confined. So that mechanism is part. But of course, physics of this one is very different. The origin of that is different.
Okay, so unfortunately we have to move on. So
Sure.
thank you very much, Keh-fei. And
Okay.
so let's keep